Hi, my name is Leah Kiner, and I am a PhD student in the Autonomous Vehicle Systems Lab at CU Boulder, studying under Dr. Hans-Peter Schaub. And today I'm going to be presenting the paper from the 2026 AAS Astrodynamics Specialist Conference titled Spacecraft Backsubstitution Dynamics for Generalized Rigid Body Component Motion. So, the motivation behind this research is the fact that spacecraft are more complex than ever. Solar-powered systems have rapidly advanced from rigid panel attachments to articulated array designs, as we can see in Lucy and Dart here. Um, and robotic arms are now dominant tools used aboard spacecraft to assist in orbital servicing, assembly, and docking operations. Some examples here include the Canadarm, which was flown on the Space Shuttle and the International Space Station, as well as the sample return robotic arm, which was deployed by OSIRIS-REx. So the main point that I wanted to highlight here is the fact that these missions would not have been possible without incredible advancements in both modeling and simulation of spacecraft systems. So modeling and simulation are fundamental aspects to the mission design process. These aspects are necessary for analyzing and validating the expected performance of the spacecraft across different phases of the mission. So it's really crucial that these simulations accurately represent the true dynamics of our system because these spacecraft are just becoming more and more complex. So with that being said, that's the focus of this research. So to model the dynamics of these systems, we first derive the equations of motion. For these systems, we can use a variety of methods such as Newtonian and Eulerian mechanics, Lagrangian mechanics, or Kaynes method. But once we derive those equations, we then must verify and validate those equations to prove that the numerical model is both correct and representative of the spacecraft system that we are studying. However, the most important question here, which is really the central focus of this research, is really how these derived equations are implemented or organized in software. This consideration has been widely studied for many, many years because it impacts many different aspects of the software, from how maintainable the software is to how scalable, testable, and efficient the software can be. So this paper focuses on the back substitution method, which was introduced in 2018. There are many different formulations out there to simulate multi-body rigid systems. This method is the most spacecraft-specific dynamics formulation. It assumes a Hub-centric spacecraft design to perform Gaussian elimination on the equations of motion, which avoids inversion of the entire mass matrix, which improves the efficiency of our simulation. And then the implementation of the spacecraft dynamics using this formulation in software is extremely modular, centralized, rapidly scalable, and easily testable. So it has all of these features that we're looking for in a favorable dynamics formulation. Okay, so kind of the backbone of this method is this hub-centric assumption. So most spacecraft which are flown into space, they have this central rigid structure, which is seen in gray here. We call that the hub. And so we can see that the frame that we assign this hub is this B frame. And so we are interested in tracking the hub's inertial, translational, and angular accelerations in our simulation. And so the central assumption of this method is that other components such as solar panels, reaction wheels, or thruster, we attach those directly to this central rigid hub structure. We also call these components effectors. And so that increases the efficiency of our simulation, which I'll show in these next few slides why that is. Okay, so here are the equations of motion for this type of spacecraft system. On the left-hand side, we have our mass matrix multiplied by our state acceleration vector, where we see our hub accelerations are those first six equations, and then our effector accelerations are grouped in those other equations. Then the right-hand side is all of other terms that are not coupled with our acceleration of our system. Okay, so this is the form of our mass matrix under this Hub-centric assumption of this method here. So our hub contributions are in the upper left in purple. The impact of the effector accelerations on our hub accelerations is in pink, and then vice versa in the dark blue is the impact of the hub accelerations on our effector equations of motion. And then the main point here for this method is that all of our cross effector contributions in this bright blue are actually zero. So we have this sort of diagonal form, which enables us to, we don't need to invert this entire mass matrix to solve for the acceleration of our system. So this slide is just kind of going over how we specifically do that. So here are our equations of our system. So we can isolate our effector accelerations on the left-hand side here, and then we can back substitute these effector accelerations into our hub, those first 6 hub equations of motion. So this gives us the simplified form here where we only need to take 2 3x3 matrix inversions using Schur decomposition to solve for our hub accelerations. So once we resolve our hub accelerations, we can then back substitute those into our effector equations of motion so that we can then numerically integrate this system. So that is the back substitution method. So next, there have been many different formulations introduced for modeling different systems, such as reaction wheels via CMGs, single, dual, and end-hinged panels. We've also seen fuel slosh models, and then also more recently, n-body sequential chains of either rotating or translating components. So essentially here in gold, we can see some of these existing components that we can simulate using this method. We have a 1-DOF reaction wheel or a 2-DOF panel. And so those general sequential chains kind of acted to act as an umbrella to enable simulation of 2 physically different components, but from a dynamics standpoint, they are the same. So, for example, a 1-DOF reaction wheel is physically different than a 1-DOF solar panel, but from a dynamics standpoint, we can use the same equations of motion to simulate both of those components because those equations can be derived in a more general way. And so those 2 formulations were recently introduced to enable just a broader range of simulation of different types of components. However, there are other different types of components that we currently cannot simulate with this method, such as helical screws or any sort of sequential motion where we want to stack rotation coupled with translation, or if we want to have rotation and translation which are not coupled, any sort of sequential joint that isn't purely either rotation or purely just translation, we cannot simulate with this method. So what this work is proposing is this new end-off general body effector or component that can quite literally simulate any type of general rigid body motion. So this can simulate an end-off rotating body and an end-off translating body, or any of those other types of motion in red. So this kind of acts as like an ultimate umbrella that gives the user the complete freedom to choose the motion of this body, however they would like. Okay, so this new formulation is for general 6-degree of freedom rigid body motion, and we use a joint mapping formulation to enable this type of motion here. So this is our system shown in this figure on the right. Right now, we just consider one general rigid body with up to 6 sequential degrees of freedom. And so we have the Hub's frame, which is this B frame, and then the frame of this general body is this G frame. And so we represent the motion of this general rigid body as a joint. So so the single joint has a degree of freedom matrix beta. And so the ordering of the degrees of freedom in beta acts as the indication of the sequential nature of the joint. And then the axis that these degrees of freedom act with respect to are the columns of this joint mapping vectrix T here. And so just for example here, we have different types of joints. And so this T matrix, each column, so the number of columns corresponds to the size of the degree of freedom vector beta. And so the number of rows is always 6. So if we have a rotational joint, the top 3 rows will be 0. If we have a purely prismatic translational joint, the bottom 3 rows will be 0. And then here's the helical screw, and then a cylindrical two-off joint. We can have a translation followed by a rotation. So we would have those other like 2 columns with zeros in those corresponding areas where we wouldn't have any motion for that specific degree of freedom. So using this formulation, we then derive the equations of motion for this general system here. So first we show in the paper how to derive the kinematics for this joint. So we have the angular velocity of the G frame relative to our Hub's frame, the angular acceleration, and then we also have the position, the Hub relative velocity, and Hub relative acceleration of this general body, the center of mass location of the general body here. And then all of these other terms are specified in the paper, but not shown here. So now that we have the kinematics of this general joint, we can then derive our equations of motion for our system. So here are the Hub translational and rotational equations of motion here. So we still need to derive the equations of motion for this general component. So here are those equations here where we draw a bounding box around the general component and then we derive these equations. So then we need to back substitute this component's acceleration vector beta into our Hub's equations of motion like I showed before. So doing that gives us this compact form. So our ABCD terms are shown here, which these are implemented in a modular way in software. And then the right-hand side, the vectrans and vecrot terms, which are not coupled with our Hub's accelerations, are shown here. Okay, so that was a lot of math. Here is just an example simulation. So we set up a 4-body scenario where we are deploying a payload away from the central hub structure of our spacecraft. So this spacecraft has 2 solar panels, which are 1-DOF rotating joints, and then the payload is a 1-DOF helical screw joint here. So we start in the stowed configuration where we first deploy each of these panels upwards by 90 degrees, followed by we deploy the payload about 5 meters away from our hub, and it completes about 4 spinning rotations as it deploys that 5 meters. So the full scenario and simulation parameters are available online. So here's just a video of this deployment here. So we can see that first each of the panels rotates upwards to deploy by 90 degrees, followed by the payload afterwards, and we're using a bang-bang control to actuate all of these components. And we can see that to conserve the angular momentum of the system, the spacecraft rotates and translates inertially to compensate for the motion of this payload here. Okay, so here are just those plots of the motion of the panels on the left-hand side, and then the motion of the payload is shown on the right-hand side. These are just the states of the panels and the payload. And then the response of the hub is exactly as we saw, where the system starts and ends at a state of rest, and then the spacecraft translates and rotates in the opposite manner that the payload deploys away from the hub to conserve the angular momentum of the system. Okay, so in conclusion, this work develops a new dynamics formulation using the back substitution method. The formulation models 6 degree of freedom rigid body component motion with absolute generality using a joint mapping vectrix and degree of freedom matrix shown here. And so this contribution dramatically expands the range of possible spacecraft simulation configurations using this method. And so we can now simulate existing components that have already been implemented using this method. And then we also have a handful of new types of motions that we can also simulate with just this one single new formulation. So thank you very much. And if you have any questions, feel free to reach out to myself or my advisor for questions. Thank you.